Hello again, Physics 30s. In today's lesson, we are going to talk about the infamous double-slit experiment. And by infamous, I mean something you've probably never heard about in your entire life. And if you talk to most people you know, have also never heard about it. But if you do know someone who's taken physics, at some point they definitely have learned about the double-slit experiment. So we're going to look at this in quite a bit of detail, and we're going to see how this experiment supports the wave model of light. Learning outcomes are to 1. Describe qualitatively how the results of Young's double-slit experiment support the wave model of light, and 2. Solve double-slit problems using the equations lambda equals xd over nl and lambda equals d sine theta over n. All right, so the double-slit experiment performed in 1801 by the scientist Thomas Young, and I've already kind of shown you the experiment. When I was yesterday using that apparatus where we were shining light through a couple of tiny little holes or openings and then trying to see what kind of a pattern we'd observe on a screen, that essentially is the double-slit experiment. We're going to describe characteristics of the experiment in more detail, but really it's nothing new. So what Thomas Young did is he took monochromatic light. When I say monochromatic light, monochromatic means light of one color. Light of one color would be restricted to a single wavelength. So perhaps a couple of wavelengths of color that come to mind would be, and this is something you should know, like the range of wavelengths of visible light. Violet light has a wavelength of about 400 nanometers, and red light goes up to about 700 nanometers. So Young takes monochromatic light, shines it through two really small parallel slits. So you got one here, one there. We call these double slits because they're a pair. And then observes what happens on in terms of a pattern that's going to be reduced on a screen. The results of this experiment do support the wave model of light because, 1, when the light goes through the tiny slits, it diffracts. When the light diffracts, it spreads apart, and that's what these beams that are kind of separating are showing. The light spreads as it goes through one slit, and the light spreads as it goes through the second slit. And now the light's going to overlap. 2, we get an interference pattern. On the screen, we get this alternating pattern where you have bright and dark spots. We're going to use a different word for it. Instead of calling it bright and dark spots, we're going to call it bright and dark fringes. Just means the exact same thing. Therefore, just by observing the fact, we get the interference pattern on the wall when Young did this experiment, or on the screen when Young did the experiment. It's enough to support the wave model of light, because the only possible way you can get that interference pattern is if the light diffracts. If the light diffracts, then it can overlap. And then if the light overlaps, you can get constructive and destructive interference that result in this alternating pattern of nodes and antinodes. One note, though, the only way you can get significant diffraction, when I say significant diffraction, I mean that the light really spreads out. As we kind of see in the illustration here, it's doing a good job of spreading apart. This can only happen if the wavelength of light is greater than the size of the slit opening. So it's really hard to show the dimension for the size of the slit opening because it's so tiny. It'd be like just this little tiny distance here. So let's say like S for like the size of the slit or something like that. As long as the wavelength of light is greater than the size of the slit, then we do get very, very pronounced diffraction. The light does spread apart quite a bit. If you want to know the reason for this, well, I'll give it an analogy. Let's say that you took a big marble and you tried to like put it through this little tiny slit. Now, obviously that's not going to happen, but let's say that the marble could deform, so it could actually like squeeze through the slit. And if it squeezed through the slit and came back out, it would like really like spread back to like its original position. So what you can do is you can kind of think of like the size of like a marble as being associated with the wavelength. So if the wavelength's really big, then it's almost like the light has to squeeze through, and then when it comes out, it spreads apart. On the other hand, if you had like a tiny marble, like a really small wavelength, if you fired that tiny marble through the hole, well, it doesn't need to squeeze. In fact, it would actually just, because it doesn't squeeze, it wouldn't spread out at all. It would just simply go through, and then it would form that one single line that we would, or the one line here we would expect if light was behaving like a particle. So long story short, if you do want to get significant diffraction or spreading of the light, then the wavelength of light needs to be greater than the size of the slit opening, or at least close to it anyways. We're going to take this apparatus and label it in quite a bit more detail. So let's start off with the light source. And again, I'm just going to bold the word monochromatic to indicate it is light of one color. And this light of one color has a very specific wavelength. I'm showing red light here, so that'd be a wavelength that's closer to 700 nanometers. I then have this wall, and in the wall I have those two openings, which we're going to refer to from now on as the double slits. We're now going to introduce a bunch of variables. We're later going to associate them with some mathematical equations. D, in this diagram, represents the distance between slits. I mean, technically it'd be like the distance from the center of one slit to the center of the other. But I mean, those slits are so small in terms of like their actual size openings that you can just simply say it's the distance from one slit to the other. No need to clarify from the center of one to the center of the other. Somewhere across the room, maybe a couple meters away, we have a screen. And now we're going to define the variable L. L represents the shortest distance from the slits to the screen, or from the wall that has the slits to where the screen is going to be located. That is my variable L. As long as lambda is larger than the size of the openings, we're going to get some good diffraction. And if we get some good diffraction, we should see a very noticeable interference pattern. So the noticeable interference pattern, we are alternating from these dark spots, which we'd call nodes, to bright spots, which we call antinodes. This keeps going node, antinode, node, antinode, node, antinode, node, and that's my interference pattern. The red spots would be my bright fringe. And obviously the dark spots are what we call a dark fringe. We're going to label one fringe specifically, though, because it's kind of like my reference point. The fringe that lines up, if you look at the midpoint of where the slits would be located, and then kind of like match that up with where the screen is, we would call that bright spot the central bright spot, or central bright spot, or central fringe, or we can call it a maximum as well. Maximum because of the maximum light intensity. We're now going to introduce another variable n, and the variable n is going to be used to identify which bright or dark fringe we're looking at. So the darker bright fringe of interest. And here's how we label it. We don't give an n value to the central bright fringe. I suppose you could give an n value of 0 to the central bright fringe, but that's not going to work out in my mathematical equations, so I'm not going to do that. So we have our central bright fringe. N equals 1 would be the first bright fringe. And again, we get an interference pattern. We get it on both sides of the screen, so it's nicely symmetrical. N equals 2 would represent the second bright fringe, or the second antinode. N equals 3 would represent the third bright fringe, or the third antinode. In terms of the dark fringes, we also need to number those as well. We label the dark fringes with 1/2 of natural numbers. So the first dark fringe would actually have a value, since it's between the central bright fringe, which I said you can kind of think of as being 0, and it's between the first bright fringe, which has an n value of 1. So the first dark fringe would have a value of n as 0.5. The second dark fringe would have a value of 1.5. Third dark fringe would have a value of 2.5. And then my fourth dark fringe would be 3.5. So whenever we look at the dark fringes, we just subtract 1/2 from that number. So for example, the 8th dark fringe would be 8 minus 0.5. It would have an n value of 7.5. Now let's draw a line from the midpoint of the two slits to a fringe we're interested in. So let's say that I'm interested in this one. I'm interested in the third bright fringe. Let's have a line going from here to the third bright fringe. And I'm going to label the angle between that line and between this arrow that's representing the distance from the slits to the screen. Theta would be the angle from the central maximum. Again, we're using the central maximum as our reference point to the location of the nth fringe. I call it the nth fringe because it just depends on which fringe you're interested in. If we suddenly changed it to the second bright fringe, then my angle is going to be smaller, because then you're only going to have a line that looks like this. So theta changes depending on which fringe you're looking at. And we'll introduce one more variable. So let's draw a line that goes from the central bright fringe, the middle of it, to, again, our point of interest. And we're going to call that variable x. X would be the distance from the central maximum to the nth fringe. And again, that's variable. It just depends on which fringe you're interested in. Again, if we went to the second bright fringe, then the x value would be smaller. So those are my 5 variables I can use to describe what's going on at the double-slit experiment, along with the wavelength lambda for the monochromatic light source. But let's talk a little more about the fringes before we get into the equations. So my bright fringes have n values of 1, 2, 3. They're just the natural numbers. Bright fringes are areas or regions where you have constructive interference occur. Again, constructive interference means that crest meets crest, trough meets trough, to give you like a much larger superimposed wave with a bigger amplitude. And in terms of light, that's corresponding to, we're seeing those bright spots. And that produces my antinodes. And again, think antinodes, amplification, or my areas where I have maximum amplification. This diagram just shows a bit more about we talked about this in the last lesson about like the path difference. So for example, you'd have like S1. We could say that's the source where one wave starts. That's like one slit. S2, that's kind of like the source of like the second wave. And we could call this point P on the wall, like a point that we're interested in figuring out what kind of interference is occurring. So once again, just remember that if we want constructive interference to occur, that if you take the path difference, PS1 minus PS2, as long as that is n times lambda, where n is a whole number, you get constructive interference. Again, as long as the path difference is a whole number multiple of the wavelength, you get constructive interference. And by the way, this might also explain why the n values up here are matching up nicely with the n values down there. Again, we'll just ignore the 0 point for now. The dark fringes are areas where you distinguish them by using n values where they're half of a natural number. So again, like 0.5 is the first dark fringe, 1.5 is the second dark fringe, 2.5 is the third dark fringe. Dark fringes are regions where destructive interference occurs. So essentially the waves are canceling each other out to the point where you're not seeing any light at those spots. And those produce nodes. Again, think nodes and nothing. Nothing in terms of not seeing any light, or minima in terms of minimizing the amplitude to get nothing. Looking at another picture, talking about the path difference. So again, we'll say this slit 1 is source 1 for my wave. This slit 2 is source 2 for the wave, and they meet up at point P, where I'm trying to figure out what kind of interference is occurring. If you take the path difference, PS1 minus PS2, and you get a value for n that is half of a natural number, we get destructive interference. And again, you can see how these n values nicely line up with the n values we're using to designate the different fringe locations. There are two mathematical equations we're interested in. And it turns out I usually don't derive equations, and I'm not going to do it right now just because the lesson has already been kind of long, and I don't want to distract from the general concept of the double-slit experiment to do some mathematical derivations right now. But I'm going to derive these equations in the next lesson because there's an important condition with one of the equations in terms of when you can and cannot use it that I really need to show the derivation for you to understand that condition. But anyways, more on that in the next lesson. So the equations I have are lambda is equal to d sine theta over n. Again, lambda is the wavelength of the monochromatic light. Or we have another equation that's lambda is equal to xd divided by nl. I'll solve two examples in a moment where I play around with these equations. Before I do that, I just want to ask one question. Let's say that you conducted the double-slit experiment with monochromatic light that was violet. Violet light has a wavelength of around 400 nanometers. And let's say on this experiment, I measured the distance from the central maximum. So I'm projecting onto a curved screen. Distance from the central maximum to the first bright spot. So that would be x. Distance from central maximum to the first bright spot, which would have an n value equal to 1. Let's say that I then change the wavelength of monochromatic light from violet to red. What would happen to this value of x if I did this? Would the value of x increase? Would it decrease? Would it remain the same? Well, we can look at both these equations to determine what is going to happen. I think the easiest one to see is equation 6. So in equation 6, the only thing that's changing here is I'm changing the wavelength, and that could potentially have an effect on x. I'm not changing d, which is the distance between the slits. I'm not changing the fringe I'm looking at, and I'm not changing the length from the slits to the screen. Therefore, if everything's constant, that tells you that there is a direct relationship between lambda and x. Well, what happens if you change the color from violet light to red light? Well, the wavelength actually increases. So if the wavelength increases, then the distance from the central maximum to the first bright spot should also increase. And indeed it does. If we actually look at this, I got these images off of that Walter Fent website. They have an app for playing around with the double-slit experiment if you're interested. That's the same website that I used the electric motor app from. Okay, so central maximum to n equals 1, and you can see my value of x has gotten quite a bit bigger, which it should according to that equation. You can also justify it with the second equation. And by second equation, I mean the one that appears first, equation 5. So in this equation, well, what's changing? Wavelength, d is constant, n is constant, theta is going to change. If theta gets bigger, then x would also get bigger. So what I would see in this equation is that there is a direct relationship between lambda and sine theta. And it turns out if you make this lambda bigger, that makes sine theta bigger, and if sine theta gets bigger to a point, anyways, to like 90 degrees, then theta is going to get larger. So second equation can also be used to justify that same observation. All right, a couple of examples. Light with a frequency of 5.45 times 10 to the 14 hertz is shone through two slits that are 0.045 millimeters apart. Calculate the angle from the central maximum to the seventh dark fringe. None of our equations we had dealt with frequency of light. So it might be a bit confusing as to what to do with the actual frequency. Well, it turns out it's not confusing at all. What I want to do is I want to take the frequency and I want to turn it into wavelength. So to do that, we need to use the universal wave equation. So that tells me that V is equal to F times lambda. Let's get the lambda isolated. So that'd be lambda is equal to V divided by the frequency. V is the speed of light. And we'll assume this is happening in air. So you have 3.00 times 10 to the 8 meters per second. Divide by this frequency, which is 5.45 times 10 to the 14 hertz. And then lambda would be equal to, let's do 3 significant digits, just because my final answer is going to eventually reduce to 2. So I've got 5.50 times 10 to the negative 7 meters. Now let's identify the rest of our variables. I'm shining through two slits that are 0.045 millimeters apart. So the distance between the slits is the variable little lowercase d. So 0.045 millimeters. I need to convert that into meters. And what I know is in 1 meter stick, I have 1,000 millimeters. Millimeters cancel off. So it's the same thing as just dividing by 1,000. So that would give me 4.5 times 10 to the negative 5 meters. What I want to calculate is the angle from the central maximum to the seventh dark fringe. Okay, so be careful because we're talking about the dark fringe. That's going to be n. From the central maximum to the seventh bright fringe, that would be n equals 7. Remember, anytime we go to the dark fringe, we just subtract 1/2. So this would be n equals 6.5. That's my seventh dark fringe. Okay, and we want to calculate theta. Of the two equations presented, only one of them actually has theta in it. So that's the one that's going to be lambda is equal to d sine theta over n. And let's get sine theta isolated. So I can do that by multiplying both sides of the equation by n over d. So I would turn it into sine theta would then equal n lambda over d. And then to calculate theta, we take the inverse sine of that, and we'll plug our numbers in. Okay, so n is 6.5. Lambda is 5.50 times 10 to the negative 7 meters. Divide this by d, which is 4.5 times 10 to the negative 5 meters. So make sure your calculator is in degrees mode, and we'll go down 2 significant digits, and it believes you get an angle of 4.6 degrees. So really, really small angle. We'll talk in the next lesson about how we can make this angle bigger, because that seems like really small. To the seventh dark fringe is only a 4-degree angle. It'd be like really, really hard to observe that. Second example, An interference pattern is produced on a screen when a helium neon laser with a wavelength of 632.8 nanometers, that's pretty much in the red range, is shone through two slits that are 43 micrometers apart. If the screen is located 2.5 meters away from the slits, determine the spacing between the second and third antinodes. Okay, this seems a little bit odd. So first of all, let's label this. Let's call this the central one. Okay, so this is the first bright fringe, n equals 1. This is the second bright fringe, n equals 2. This is the third bright fringe that is n equals 3. And what it wants me to do is it wants me to figure out, well, what is the distance between the spacing or distance between the second and third antinode. So that is x. Problem is, like, the way we define x is from the central antinode, but it turns out, well, what would be an equivalent distance of x if we measured it from the central antinode? The distance from the second to the third antinode would actually be the exact same distance as going from the central antinode to the first guy. So that'd be the same thing as going from the central maximum to n equals 1. That's equivalent to going from the second bright fringe to the third bright fringe. In fact, we can state this. N equals 1 anytime you're looking at the distance between, I'll say for adjacent antinodes. So bright spots 2 and 3 are adjacent antinodes. They're beside each other. Well, I mean, aside from the dark fringe in between them. Or for adjacent nodes. Like if you went from like the first dark fringe or the 7th dark fringe to the 8th dark fringe, it would also be a value of n equals 1. All right, what else have we got here? Yeah, let's highlight that word adjacent. We know the wavelength. It's in nanometers. To go from nanometers to meters, you multiply by 10 to the negative 9 meters. So you have 632.8 times 10 to the negative 9 meters. And what else do we have? The slits are 43 micrometers apart. Micrometer is times 10 to the negative 6 meters. Millimeter would be 10 to the negative 3rd meters. We know that the screen is located L, 2.5 meters away from the slits, and I want to get X. Again, X being the distance from the second to the third bright spot, which is equivalent to the same distance from the central antinode to the first bright spot. This time around, since we don't know the angle, we're going to use the other equation. So that's going to be lambda is equal to xd over nl. We want to get x here, so x would be equal to lambda nl, all divided by d. Let's plug our numbers in. So we got 632.8 times 10 to the negative 9 meters, multiply by n, which is 1, multiply by L, 2.5 meters, divide by D, which is the distance between the two slits, 43 times 10 to the negative 6 meters. And then we get X is equal to, we're doing two significant digits here, so that would be 0.037 meters. Or if we turn that into centimeters, you just multiply by 100, so that'd be 3.7 centimeters. That's it for this lesson. And if you'd like, you can complete the assignment called the Double-Slit Experiment. And next lesson, we'll talk about a device called the diffraction grating And we're also going to look at the derivation of those two equations that we used today. And I'll talk to you then.